In this video, I will explain you two important terms in magnetism. These are magnetization and magnetizing intensity. First, I will explain what is magnetization. Certain elements do have magnetic property. Certain elements doesn't have magnetic property. What is the reason for this? In current electricity, we have learned that when we have a conductor in this pair, we know that very large number of electrons are there inside, and these are moving with thermal velocity in random direction. Even though we are not providing a potential difference, even though we are not providing a battery across this. But why we are not able to measure current across this? We are having electrons moving, right? So that is supposed to be the current, but we are not able to measure it because whenever there are one electron moving in rightward direction, there is a chance at some other position that electron will be moving in leftward direction, making the net effect zero. When one moving in upward direction, another one will be moving in downward direction, making the net effect is equal to zero. The possibility is very high because a large number of electrons are there. When one moving in this direction, somewhere at some position, one is moving in this direction, making the net effect is equal to zero. So that is the reason we are not able to measure current across this conductor when the potential difference is not provided. But when we are providing a potential difference, what will happen? We can align all the electrons moving in one direction. Here in this case, we can measure a current between the conductor. So it is the same concept here. See, with this concept, here it is little bit different that certain material do have magnetic property by nature. Certain material doesn't have magnetic property by nature. Now, the reason for magnetic properties or magnetic intensity we have learned in moving charges and magnetism is nothing but movement of charges. Whenever a charge is moving in a space, that creates a magnetic field around that space. So when a current is moving, the magnetic, let's say this is electron moving, the current will be in this direction, so here magnetic field will be into the plane, coming from the plane. It will be circular around this moving charge. Now, how can a substance produce magnetic field around it when there is no movement of electrons here? Actually, there are movement of electrons. In an atom, see, these substances are made, these specimens are made with atoms, right? In an atom, we have a nucleus, and around nucleus we have orbit. The electrons and charges are moving, are revolving around the orbit. So in the orbit, they are moving in circular motion. Across the orbit, they are making the motion. So these are movement of charges. These are moving charges. Now this creates a magnetic moment. But if that is the scenario, then every substance is made up of electrons. Every substance is made up of atoms, right? And that has electrons in their orbit. Now, every substance should have a magnetic moment, and every substance, like a pen and other substance, everything should behave as a magnet, right? But here in this case, the same case. Now, whenever there is one magnetic moment created in this direction, there is a chance that another magnetic moment is created in this way, so that the net magnetic moment is cancelled. But here in this case, in certain elements, magnetic moment will be randomly placed, randomly oriented in this way. That is upward, downward, then in this way, so that the net magnetic moment is zero. But certain elements, they will have a net magnetic moment in this direction. If 4 in this way, 2 will be in this way. We will go to the reason in depth in coming videos. So certain elements, they do have net magnetic moment by nature, but certain doesn't have. But actually everything are having magnetic moment inside, but the net magnetic moment when we are calculating, only certain do have, certain doesn't have. Now I am going to talk about these elements here for magnetism. So by nature it is having a total magnetic moment of m. So next I am going to represent it as small m. Okay, only for this case. Okay. Basically, I'll be representing it as magnetic moment, capital M. Okay. So here I am going to represent it as small m. Now, magnetization here I am going to take it as capital M. That is equal to, as been defined as M net divided by. Now, how I can only compare two substances to measure which one is having higher magnetization by taking the equal volume. For example, so let's say this one, the whole thing is one substance and this one is another substance. Now, obviously, this will be having higher more magnetic moment. Why? The total size is higher. But can I say that magnetization is more in this substance? No. I have to make it in common volume, then I can, the same volume, then I can compare these two things. Okay, so I am taking a volume here and same other volume I am taking. Now I am comparing here what is the net magnetic moment, what is the net magnetic moment, dividing with its volume, dividing with volume, then getting the value of capital M, I can compare magnetization is more in this substance as compared to this substance. Okay, so that is the reason we are dividing this volume, so that now this has become quite standardized. Now I can compare one substance has got higher magnetization and another substance has got lower magnetization. Okay, now, so magnetization has been defined as net magnetic moment divided by volume. Okay, now this is magnetization, right? Now how to get magnetic field inside the substance that has got M magnetic moment, M net magnetic moment inside, that can be measured with this B is equal to U0 into M. So M is magnetization, that has been defined as M net, that is net dipole moment, that is magnetic dipole moment divided by volume. Now, if you know this value, to get magnetic field inside those substance, you can use this equation. Dm is equal to mu0 into M, where M is magnetization. Now, next concept is very important, that is magnetizing intensity. Now, the name itself is suggesting that this is magnetizing something else. Okay, so with magnetizing intensity, we can magnetize certain other material. For example, now here magnetic moments are oriented in this way. But with certain magnetizing intensity, I can magnetize this substance. Now it is not having any magnetic property. Okay. Now the moment I bring a magnetizing intensity here, now this can be aligned. So this can be magnetized. See the name? Magnetizing. So it can be magnetized. I will explain it. Okay. I think it will be a bit confused here at this point, but after this explanation, it will be more clear. Okay. Listen here. Now, magnetizing intensity means it's an input, it's a source. With the source, we are magnetizing a substance. Now, we know that here in this case, in a solenoid, what is the value of magnetic field in the axis? We have learned it as mu0 and M, where N is number of turns per unit length, I is current passing through it. So mu0 into Ni is the value of magnetizing. It's the value of what magnetic field here. But basically, this intensity has came from these two values, N into I. I will explain it why it has came from N into I. See, what is mu0? Mu0 is the property of this media. That is the permeability of this space, right? Now, magnetizing intensity I can only change by having more number of turns. That is number of turns per unit length. So instead of using a solenoid in this way, when I am using a solenoid in this way, my magnetizing intensity will be more. Why? I have changed the number density. That number of turns per unit length. So this can be changed. Now I can pass higher amount of current through this. That will also increase the magnetic field in this medium. So other thing that is purely depends on the medium. That is not depends. This is the input, right? Solenoid. I can change the number of turns. I can change the current passing through this. So that is the two things I can control. That is the magnetizing parameter what we are giving as an input. So this Ni is taken as magnetizing intensity. H is equal to magnetizing. So So this is the input given. Now with this magnetizing intensity, it is creating a magnetic field in a medium. What is the value of what is the value in the medium magnetic field? That is mu0 into Ni. So with an H magnetizing intensity, H is nothing but Ni, we are creating a magnetic field of mu0 into H. So here the input we have given is H. With that H, the created magnetic field here is mu0 into H. Now with the mu0 into H, now using this substance can be magnetized. Now let's say using this magnetic field, now this substance, previously it was having net magnetic moment as 0. Now it has got some magnetic moment. If it is getting a net magnetic moment M net, then divide it with M net, divide it with volume, we will get magnetization. Okay, I will repeat it. This is the input. H, Ni is the input. That is the only thing we have in control. Okay, so with H magnetizing intensity, we are creating a magnetic field in a free space, that is V0. What is the value? mu0 into H. We are creating here. With that, an object has got magnetization. So how can we measure the magnetization in the object? That is by measuring the total magnetic moment created with the volume. So M net divided by volume is the magnetization in this substance. Okay. Now, if M is the magnetization, we know that magnetic field created inside the specimen will be mu0 into H. See, which triggered which one here? mu0 into H has triggered mu0 into H. H current passed through a solenoid. H magnetizing intensity we have provided. So this has created a magnetic field mu0 into H. With that magnetic field, this has created a net magnetic moment, and that is M net, that has been measured with respect to volume. That is M net per unit volume is magnetization. Now the magnetic field inside this is mu0 into H. Now I am going to redraw it. So solenoid, what is the magnetic field inside the solenoid? mu0 into H. Now when I am keeping a magnetic substance inside, it has got a magnetization of mu0 into. So M is the magnetization. Now the magnetic field created by the material is mu0 into M. Now this is created by force. So now this material has got mu0 into M magnetic field inside. Now solenoid is giving mu0 into H inside. So what is the total magnetic field inside? The total magnetic field inside is equal to mu0 into H plus mu0 into, that is basically B0 plus B. So B0 is defined with magnetizing intensity mu0 into H. mu0 into M is magnetization. So don't get confused. This is magnetizing intensity, that is H. With that we will get magnetic field in a free space. With magnetization, the value is capital M. With that we will get magnetic field inside a material. Adding these two, we will get the net magnetic field. So this will be the value. So B is equal to, these two are very important. So one thing is H is important. What is that? Magnetizing intensity. M is important. That is magnetization. So learn these two, and after that with the concept get this equation. Thank you.